So today we're going to discuss about the fifth chapter for induction motor. So this chapter try to focus more on the control method. Last week we already discussed about the voltage control, basically how the equation look like for the voltage control and how we polish the equation using the equation circuitry, and then we can develop the torque equation. Most importantly will be the torque equation. You do need to memorize how to look into the torque equation, how the torque equation related to the voltage, current, and the slip and the R2. That's an important component for a torque equation. So that's also one of the most important equation for the induction motor too. So for chapter 5, we're going to look into more in the control method. So in here, you can see that, so how do we control the motor voltage to regulate the motor speed? So last week, we mentioned about the motor voltage. So the voltage and the frequency and ratio is something related to the magnetic flux. That will be different from the conventional DC motor. Conventional DC motor, we tend to use the magnetic flux circuitry to control the motor flux. But in here, we know that motor flux is roughly proportional to the voltage and the frequency ratio. That's to say, if a motor is running at 460 volt and the frequency is 60 hertz motor, then this ratio 460 and 60 hertz will be related to the flux level. So we usually tend to keep in this voltage level. But how do we control the voltage in here? Do we have any typical method we can control the motor voltage? So probably we try to use the inverter to do the job. So that's to say we're able to use inverter to control the motor voltage. But usually if we just supply it by our power line, say our line voltage here, 190 volt or 80 volt, then this voltage is fixed voltage. If you want to control voltage, we have to use a kind of the, say, transformer and maybe potential divider. But that is not a good method because we're wasting the energy there. So that means the most popular way we have to do is use power electronics to control the voltage. So another method is to control, we need to examine what the theory behind why we need to control the frequency too. So later on we discuss about the theory, why we need to do the frequency control, how we regulate the input frequency to the motor. So we are not just using 60 hertz because 60 hertz are more related to 30600 RPM. If we like to use other frequency operation, we need to control the input frequency too. So later on, I will show you some theory why we need to do that. So that's how we understand about the motor control here. So in this chapter, we're going to look for a number of areas. Firstly, voltage control, why the voltage control we needed here, and how do we control the voltage in the induction motor. And then we're looking into how the frequency and voltage correlation. So that will be an important and simple correlation between them. And then we're looking into by using these two methods, we are able to regulate the motor speed, how to develop the speed controller. Besides the speed, we also need to examine about the motor torque. Motor torque, of course, everything we highly relate to motor torque. If we want to control the speed, we first need to control the motor torque first. From there, we can regulate the speed. So usually for motor control, we have a number of the control loop. You haven't done too much about the control system yet, right? Are you learning now the control system? When are you going to do that?
Next semester.
Right. So in the control method, then we have a very type of the control method. Now you all know about the PI controller, PID controller. That's only the controller. But the controller loop, we do have a different kind of controller loop. In here, we're going to show you how that can be done. The teaching here, you don't really need to under the control theory here. You just look at the diagram, you know how the control schematic look like. So in here, we do need to control the current. We also need to control the torque. We're going to show you the correlation between them. And then section 6, we're looking into the one rotor induction motor. We did not spend too much time up on this motor because we mainly focus more on the screw cage induction motor. But this induction motor is also one of the popular induction motor too, beside the screw cage. Although screw cage is more popular, but this one rotor, we're able to connect with the rotor circuitry to external system. So in this case, we are able to regulate the rotor circuitry by using resistor or by using some power electronic to do that. Rather than at the moment, what we discussed here, the screw cage are mainly a closed circuitry. We do not connect anything. Of course, screw cage will be a simple, easier to control. But when we able to connect the rotor circuitry for some of the circuitry, more look like a rotating transformer, you can do a bit more for the rotor circuitry. We know that for the motor torque is related to R2, rotor resistance. So if we're able to connect the rotor circuitry to external circuitry, we're able to control R2. So then R2 control appear in section 6 and 7. We try to look into how we control this special type of the motor. So this motor is still really popular, especially we find them really useful in certain motor control, especially in renewable energy power generation, like the wind power and also the hydropower. We use them really, really often. And then next, we're going to conclude the discussion. So let's look at one by one then. Of course, in the coming Wednesday, we are not going to cover this chapter. So we mainly cover the previous chapter 1 to 4 for induction motor. So most of motor, we tend to control the torque and also the speed. Same as in the induction motor too. In most of the induction motor control system, we try to control the motor torque and motor speed. We do have a number of mechanisms how to control that. So in here, I will show you a number of simple control loop method. We tend to use them to control the motor torque and speed. But one of the most simple method is to control the motor speed using the voltage. Although we are not feeling really comfortable only to control the speed using the voltage, but that's one of the simple way. You can see that for some really simple induction motor or low power one, or like the fan slow cooling system, we can just use the voltage to do that. So later on, we can see how we are going to do that. And although we know that most of the control loop, we do have it consist of two control loop system. One will be the speed loop, another one will be the motor loop. So you can able to see two of them working together. And later on, we'll show you how we can construct the loop. And of course, we're going to discuss about the round rotor. So that's also important in this motor. So we're able to connect the rotor circuitry to external. So that can be done by the resistor and also rotor inverter. Of course, using inverter is really for something simple and low-cost development because we use resistor to regulate the speed. Obviously, you see that this method, you're wasting energy. So of course, the proper method to do will be using an inverter, which is able to regulate the energy and use the inverter to process and then return energy to the microgrid. So here we'll give you a very simple, conventional and old-day method how we control the motor speed. You see here is a fan low, so that means that mainly for the cooling. So this kind of fan low, probably we don't care too much about the efficiency or energy conversion. We only care about too much about more on the control the speed. So you can see here we can use kind of the regulation of the input voltage by using more look like a transformer. You see in the old day when we don't have the power electronic to control the voltage and the frequencies, then the only thing we can do is to using some method, potential divider, to regulate the input voltage. In here, we're using an auto transformer. Before auto transformer, some people may use resistor, potential divider of resistor to do the job. That even worse. So auto transformer is one of the way we can do that. You can see that this kind of auto transformer, you do rely on how good the three winding are being placed. You see sometimes the winding are not placed properly. The voltage for each winding may not be exactly the same because we talk about three-phase voltage balance. If the voltage is not quite balanced, so we may end up with some kind of issue. So we also rely on the balancing. we never can ensure that mechanical construction can have a really good balancing. Of course, when we use inverter, we do have some detection to detect the pulses. We can make sure the pulses are balanced. But of course, mechanical, it all depends on the system. When the system getting aged, some of the winding may have short circuit, one or two. Then in this case, we may also have unbalanced voltage too. But this show you really simple voltage control for induction motor. Fair enough, you can see that how a voltage control look like. Basically, show you can just using the voltage to control the motor speed. How we control motor speed for the previous chapter, we show the basic theory and the equation. So in this chapter, we show you the schematic, how they look like. So if you attend the last lecture or to see the lecture looks, then you see briefly about what's the method we use for voltage control. Then using voltage control is not good. Using auto transform mustn't be a good method. So we use so-called the 5-Richter chopper. So 5-Richter chopper is just more look like chopping the voltage. So how it look like will be for instance, we got sine wave in here. So if we don't disturb the voltage, then will complete sine wave apply to them. But using this 5-Richter, we can, for instance, this for the forward current, that's for reverse current. Then we can just allow a delay in here. Then of course we call it the phase angle control. So we don't turn on the transistor, but we turn on other certain phase angle. So in this case, this average voltage will more look like reduced voltage. So that means the voltage waveform probably will therefore become like this. Like this kind of the voltage waveform. But very speaking, this waveform will be further, not only this one, because there's some inductive component here, and the waveform may not be only this, may also look like something like this, depend on the inductor behind. So at least you can see that some of the voltage are missing in the input voltage. We therefore reduce the voltage. So this thing we call it the chopper, mainly it just look like it's chopping the voltage in the input side to reduce the voltage. And the component we use here, we call it the 5-Richter. I'm not quite sure you learn about the 5-Richter. Basically, I think you learn about the 5-Richter operation. Have you learned them in the semiconductor? No. 5-Richter is more look like a dial, but we're able to control the angle of conduction. So the 5-Richter, this is the gate. You see, when we have this one, this called a gate. So we need to supply voltage to the gate in order to conduct the 5-Richter. Yes?
That's the question. Is the window that kind of chops the portion of the input voltage, is that a period that's in phase with the original signal, or is it separate?
So when you see you got firing circuit here.
Yeah.
That firing circuit, we need to measure how much we delayed. So that means we can delay by 10 degrees, 30 degrees, whatever degree, that degree control the average voltage. Actually, the voltage after we delay them become this voltage. So obviously you see that average voltage become less, so we can control the voltage. So the firing circuit is just a single pulse will be sufficient. So if you don't fire the gate here, this 5-Richter will not conduct. So when we fire it, the 5-Richter will start to conduct. The behavior from the 5-Richter is quite special. It will not turn off by itself. It only when it turn off when its current drop to zero. So that means, for instance, if the voltage drop to zero, doesn't mean the current drop to zero. But if the current drop to zero, you terminate this point. You learn more detail about this power electronic device when you go my class in power electronics. Sorry about that. The system asked me to teach you here. So, but bear in mind, it's quite straightforward. For 5-Richter, basically will be look like a dial. If there's a dial, we got a full sine wave. But because 5-Richter, we only trigger, we call it trigger. And a final pulse in here, and then you only contact that point. probably let's say 30 degrees, and later on another 30 degree, 180 degree, in terms of obviously this voltage become less. So we can control this angle, which coming out from the final circuitry, we therefore reduce the voltage. But strictly speaking, the thyristor will be turned off by itself. We cannot turn off by using gauge bicycle. So it's very special devices. So when it turn off, when the current pass through them, equal to zero. So then at that point, if the current just equal to zero, turn on by itself, but if it's inductive, the current will try to hold conduct a little bit more before we finish the conductor. So that's why this can this waveform or can this waveform. But anyway, you can see that we are using the phase angle here. You can therefore reduce the voltage. So that's what I can tell you. Any question up to this point for thyristor? Thyristor is really famous so and it developed much earlier than MOSFET, IGBT, and bipolar transistor. Once, I think, after 60 years old, when people started work on semiconductor, we firstly developed the diode and then the thyristor. That's a marvelous because at that time we were able to use thyristor to control how much current pass through. So that's something quite special. Probably in 1960 something, probably happened exist yet. So when we send the space shuttle to the moon, the computer we're using and also the controller we're using are using thyristor here. So quite interesting. And then there's a battle during that time we just developed semiconductor. I think the people still using the cathode ray tube. I'm not quite sure you understand anything about the cathode ray tube. Another control system and control the current, control the voltage. And then during that time, two kind of argument. We're not quite sure during that time, cathode ray tube will be winning the market or the thyristor. And then the US try to work on the thyristor, and the Russia trying to work on the cathode ray tube. And then, of course, cathode ray tube disappear from the whole world. We have all working on semiconductor. So anyway, so that's how the thyristor works. So we use this thyristor to work on. Then you may ask me, do you think the thyristor still using it extensively? This circuitry is a very conventional circuit. We use it for motor control. And this circuitry has been using another fence control. You can be able to even though at your house, and you try to have a control button for the fence speed, and then we are using this thyristor control. It's still quite popular, even though for your cooker at home. Then of them are using this thyristor control the voltage going in the output. So that is to say not only for motor speed control, but also for heating control, thermal control. And mainly here you can chopper the angle, so that's why I call it chopper. We can reduce the voltage. Thyristor is one of the really popular device. The thing is really stable, very robust, so much better than all the transistors you can see, much safer, more robust than bipolar transistor, like those BJT you learned in the past. Do you know BJT?
Yeah.
Yeah, BJT, MOSFET, IGBT. So thyristor are much more stable. So that's why we're still using them for many operations, including the train. So many of the cross-country train are still using thyristor to control the motor because it's highly stable. And also the power, voltage, and current are much higher than all the MOSFET and IGBT. So that's why we still heavily using it. So that's why in here, this page will show you we're using two thyristor to control bidirectional current. Basically, one thyristor only control unidirection. So now we're using two thyristor, putting them in anti-parallel, then we're able to control the bidirectional. So this, the jargon we call it anti-parallel. So each varistor, as you see here, are fired by particular pulse. So usually single pulse will good enough to fire it. So that means to say, if we look at here, then in here we have single pulse. In here we got another pulse to trigger it. So that's what we need. Single pulse was sufficient. But of course, we sometimes in control circuitry, we worry about single cell, we may misfire due to some error. Then we using a string of pulse, quite a few pulses here. Make sure we can turn on properly. So that's a implementation technique. So that means we got two pulses for in here for each of the phase, right? So that means they display by 120 degree anyway. So the advantage, of course, this method will be simple and low cost. Varistor usually will be much lower cost than other IGBT, and the control circuitry are simple. But of course, the disadvantage will be this waveform. You can see that consist of this kind of the chopping. That means there will be harmonics. Usually we consider a good sine wave will be less harmonic. But when we construct a sine wave not using a pure sine wave, but using a chopping in here, then not the so-called low order harmonic. So probably you got 5, 7, 9 harmonic that may influence the power distribution. The power distribution of grid system or PG&E doesn't like this harmonic. So probably in the front end, you may need to have some filter to filter this harmonic so that this voltage will not influence to your PG&E. So that is to say, this kind of filter, some people may use power factor correction, which is to do some kind of load. So more professionally, people sign we have to control the power factor. The thing is, you may not understand too much about power factor yet. Do you know what power factor is?
No, it is.
Okay, good. So power factor mainly try to make sure the voltage and current are in phase. So that means we don't have too much. So voltage and current in phase. So that's the first basic principle for voltage current in phase. That's to say, and there's no room to. But I can write this pen still working. So the voltage here, if able to ensure the current also in phase, then the power factor will be opposed to 1.0. That's all we want, right? So that means if we are drawing current from a resistor, then that will be power factor equal to 1. So that means if our AC source here, if we connect to a resistor, then obviously the power factor you can see here opposed to 1.0. But not only this is also the basic principle what you learn from the circuit theory. But more importantly will be we also have another important component for power factor, which is harmonics. Even though you can see that this waveform more look like the voltage and current could be the same kind of the phase, but we are missing this part here. So this is the harmonic come from. So this voltage will have high order harmonics. So that means another system here, the power factor depend on firstly the angle, the cosine phi. So there must be a component there. Another component will be related to the harmonic. Yeah. So that means when the harmonic is higher, then we have a poor power factor. So that means that's how this harmonic comes from. So this voltage waveform, the problem because the harmonic may not be too good anyway. So that means this. So when you learn in circuit theory, they usually mention to you about the cosine phi, the phase angle. But more importantly, will be harmonics. They also contribute to the power factor. When systems have a poor power factor, which PG&E don't like that, they will charge you the harmonic out. So that's why before this system, we connect to the PG&E, we need to put some filter, maybe power factor correction, or the PFC. power factor. So this a PFC power factor correction is a really important system we tend to use. So it's able to control the base angle between voltage current, and also control harmonic with loads possible. So that's all we do. So that means in here you can see that in this data and solid state voltage controller we call it, because we use thyristor, it's simple, but however the disadvantage will be high order harmonic. When harmonic is high, that means the power factor is also become lower. So that's the thing we don't highlight. But fair enough, it's simple, low cost, robust. Whenever we use thyristor, the circuit will be really robust. Why is that? Because thyristor, firstly, it can stand for high voltage. Even though thyristor rated at, say, 500 volt, even though sometimes apply for 700, with 1000 for a short period of time, is still quite okay. The current as well, sometimes over current by 10%, 100% for a short period of time, still good. So that's why I call it robust. So this kind of circuitry is really thyristor. We call them robust. So that's how we can define the operation for thyristor. So so that's why for control the speed, so we need to use thyristor to control the firing angle. But how that firing angle look like? Angle sometimes we use symbol for alpha for firing angle. Then we usually measure the speed here. And then we will set up the speed, and then that will have a control system. So that controller, we haven't learned how to develop the controller yet. We have controller to control how to refine the thyristor. So probably when the speed is not sufficient, then we need to have higher speed, then we increase the voltage, then we decrease the firing angle, and vice versa. So that's the basic way we can do that. So that's only show you a simple way to do that. So that means when the speed, when n is lower, then firing angle, we can therefore lower the firing angle in order to control the speed to what we want. Any question up to this point? I think this kind of schematic are quite straightforward. You all can imagine, can work out how that can be done. So most of the control loop, they usually have this kind of so we call it control loop. So this one only a single control loop, only has single, we call it the speed loop here. It's also called the speed loop. Obviously, you can see that one single speed loop, we're not able to control it really well, because in this loop here, we only control the speed. To control the speed, we through the firing angle to do that. But if you can see that the output at some other requirement, like a torque requirement, if suddenly a torque requirement has changed, then we may not able to respond so quickly. So that's why many of the motor control system, we also control the motor torque too. So we can see some system may have more than one control loop. Beside the speed loop, we also control the torque. Some motor also control the fuel. So there's many different configurations. So this one to show you a simple method how we control the motor speed. Then just now we mentioned about how we control that. But you see one of three way will be so-called how to control VF. So that's to say, you can see here, then that is the magnetic flux equation. We all know about that. So you can see the voltage are actually related to the frequency and related to the flux. So that is from the V2 when we work with the transformer. So from here, we can see that the magnetic flux for any magnetic circuitry, including transformer and motor, is proportional to voltage over the frequency. So that's to say, if we want to control the constant flux to a motor or motor, I like it to working at the optimized flux value. Any motor, then you know that the best performance of the motor flux, you perform better. So in this case, if a motor, you find a certain voltage and frequency ratio, then we use the same ratio, then we usually have the best performance of the motor thrust. So that's what we're trying to do. So that's to say, if you want to control it, then we need to we have the VF control is one of the popular method we tend to work on. And then this method, we call it constant. Constant VF control is one of the method we have been using for many years for control induction motor. So constant VF control is one of the good ways we're able to control the motor system. So it shouldn't be control VF control, it should be constant VF control. So you can see in this diagram, if we want to control the voltage, then basically we tend to work on even voltage across the magnetizing proportional to F. So E over F in here must be constant. But the thing is, we don't know the internal voltage for the motor in the T model. We do have a voltage drop on R1 and X1, which we don't know what it is. So that means, but however, we know that under normal operation, this voltage would be really close to this one. The voltage drop on here would be negligible, very small, maybe just up to 10%. So usually we can still approximate the control method by using E voltage instead of E voltage. So that should be good enough. So that's why we just call it constant VF control. We use VF control rather than EF control. That should be good enough. So if you look at many literature, then the constant VF control is really popular. Constant V over F control is one of the really famous and control method for induction motor and also for some other motor too. So the important information for this page will be introduced to you a constant VF control. Basically, come from this simple magnetic equation. And then we try to say E over F should be always constant. To do this one, for motor operation, simple method, we can achieve the voltage drop on the leading inductor and also R1, the copper resistance to be negligible. Then we can use the V1 voltage, input voltage. Where to approximate, so then you can approximate by using V over F. So that's to say become V1 over F equal to constant to develop the control method, how we control the motor. So that means V1 over F is a constant in order to control. So that's a simple enough. So now then, if you look at the diagram, obviously you can see that the control diagram will be like that. The voltage and the frequency would use proportional to each other because we are using constant VF control. We can draw a straight line to it, but the question will be why the curve does not pass to the origin? Why is that? It's proportional, right? Why do we not passing through the origin? What do you think?
Well, if they're proportional, then the only way for it to be zero would be equal to there's no voltage going through.
So if you're not passing origin, what is the line intersect? What the parameter we use in the line intersect? If that is correct.
One.
Sorry?
One.
One? Where does the one come from?
That would be this.
Any other recommendation? Any other part of this gentleman? Want to make sure. I'm sure about network drops and let's go. Yeah, that's not lecture about that. The thing is, from this model, we only know the voltage here. Our VF control, we only control this voltage. And the frequency, we cannot control this E voltage, this internal. Nobody knows. We cannot insert a probe inside the platform. Even if we insert them, if this location does not exist, motor will only have stator winding and motor winding. This call only for motor imaginary point. Does not exist anywhere. So that means if you use this voltage, we have voltage drop on here. So if you use this approximation method, you see this is also an approximation. We tend to say the primary thrust is proportional to the V1 over F1. So that's the primary side. In the primary winding, the whole circuitry, the T model, are referred to the primary side anyway. So we say this primary flux is of course proportional V1 over F1, but more strictly speaking, this should be E, right? More accurately should be E, but we can't do E anyway. So we have to use V1. So this voltage drop will be equal to drop on the R1 and X1, right? So that's what happens. So that means we need to do something. We need to add on something in on the compensation. So that is so-called why we have this kind of the winding set. So this voltage. So that means in theory, this will be a parallel 50 degree, and this amount of voltage, we call it the boost voltage. So this voltage mainly to boost up the proportional voltage slightly by a certain amount. So this voltage try to compensate for the voltage drop in R1. So that's common technique. So you see this technique just only a so-called empirical method. By experiment, you can see that you look at some voltage. How much voltage, of course, it depends on R1 voltage drop. In theory, you can calculate exactly, but the R1 voltage sometimes depend on the current, depend on top. It can be varied. So that means your controller need to estimate the total voltage in here. So that means there's no fixed answer, 10%, 5%, but we usually increase something to ensure that we will have a good magnetic flux. Many controllers, we just increase it by 2% to 5%, especially in the low voltage side, in order to compensate for voltage drop due to the leakage component and also the R1 resistance. So that's a really typical method we work on the induction motor. If we don't do that, what will happen? If we make the line crossing the origin, if we don't put the post voltage, we have you won't have. What do you think? Still work or what do you think?
Yeah, with the motor stops and just stops being voltage and that's just kind of stops where.
Exactly. If you do that, then your applied voltage, you never can deliver to the E1. You see the motor with this E1 voltage to produce necessary mechanism is the sustain the motor, the air gap flux. If the voltage already being dropped by here, you try to produce some current here, the voltage already cancel out the V1, you have no voltage here, no magnetic, the motor is not starting. You can't start. So that means if you cannot see the motor start, and then you're going to increase slightly the input voltage until the motor start, then you see if the speed in the top will be visible. That is your post voltage. So you can test the motor by experiment to try and error. You can do that. Of course, you can using a more complicated model to calculate the voltage drop, vary with the current in the top, and then you can calculate it. That's more complicated. But for simple motor control, you can just use up 2%. Even though you overestimate the voltage, so what? It's low voltage, you won't burn the motor. So that's still quite helpful. So that's one of the simple methods you can use for motor drive to do the job. Especially in here, we do have the outside control loop, the speed loop. You won't overspeed the motor anyway. But using this method, you can make the motor start. So that's how we do the motor control. It's a very simple method. We're able to control motors start properly. Any question up to this point? Simple, right? This motor control are quite straightforward. Yes.
The frequency F, is that the stator frequency or is that the switch?
Okay. So that's why I use F1. F1 is the one mean the stator, two mean rotor. Yeah. In my rotation form. So let's see an example to see how we deal with this kind of the simple voltage control or constant VF control. So we have an induction motor, 3-phase, 4-pole, 460, 60 Hz as the following parameter. So the R1 is 0.8 ohm, and then rated current 25 amp. The rated slip is 4%, 60 Hz, and the base voltage 460, which when we mention voltage must be 9 voltage. we seldom talk about the phase voltage. So the motor now operates in constant VF control from 6 Hz to 60 Hz. So let's calculate the idealized VF curve at 60, 30, and 6 Hz. What's the ideal voltage? And the actual voltage required to compensate for R1 voltage drop, and also torque capability at 6 Hz with and without a compensation. So that's an interesting part. And we require boost percentage at low frequencies. So let's think about it for 1 minute to see how we're going to do that. So that is to say, if we go for this one, we first need to calculate about the boost voltage, the requirement voltage at the low frequency. Usually boost voltage is important at low frequency. High frequency also high voltage doesn't bother us. So of course, we are still calculating boost voltage requirements, but low frequency and 60 Hz will be more important without that compensation. That compensation means the boost voltage. So to do this one, I think we need to calculate boost voltage amount. But how to calculate boost voltage amount? We know that V over F is constant. So that means for the 60 Hz over 60 Hz will be fixed. When we move along the voltage, then we still figuring this ratio. But this ratio has some kind of the issue because the 6.60 volt is not the V voltage. The V voltage is more internal voltage. So that's a consideration. We need to think about this question. So let's see my solution. Firstly, we need to work out the constant VF ratio. So that means the ratio V over F with 460 over 60. So that means whenever we do any voltage or frequency variation, we need to keep this voltage rating. So that means at 60, this one at 30, 230, at 6 Hz will be 46 volts. So in theory, when we use constant VF control at 6 Hz, we use 46 volts. That's what we're trying to do. So that's the important part. And then let's calculate voltage drop. You see the current we are using 25 amp rated. So we can have all, because for constant torque control, right? We can always the current 25 amp anyway. 25 amp, but the resistance will not be changed. It's a fixed component. So that's to say in here, the primary side voltage drop due to the R1 resistor is this one. So that means 25 times 0.8 ohm will be 20 volt. So 20 volts is the voltage drop, but that's only the per phase parameter. Per phase, so we multiply with 3, then we can able to get the actual voltage, 9 to 9. So that's to say, any voltage, we should have this voltage drop due to the R1 resistor, the full current condition. So that is in theory, we should add this voltage to the motor on the top of the proportional ratio. So now then, the next thing to do, we add up this voltage. So if we do that, then our ideal line voltage using our proportional, yeah, that's a proportional ideal voltage, right? So that means 6 Hz will be 46 volt. And then adding the voltage, that will be resultant voltage. So that means we tend to boost up the voltage on here. So that means you see 46 at the boost voltage become 80. So we cannot using 46 because voltage on R1, we need to use 80 volt to do that. And then coming with our problem here. I think 6 Hz will be really reasonable because at low voltage, all the voltage is here due to R1. But how about a high voltage, 30, 60 Hz? Can we still adding such a high voltage to the motor? Probably not, right? The motor will go up such a high voltage. Yeah, so that means you can see that the curve here. Yeah, this curve we only joining 2 points. One originally from origin to the 460, but when we have boost voltage here, this point is joining also 460. You see the motor already allow the 460 volt to compensate for the voltage drop at R1. At high voltage, the sharing for that kind of R1 voltage will be really too concerned to the motor facility. So that means usually for motor drive, although for theoretical calculation, we need to add the boost voltage. So we in theory we need to add this kind of the boost voltage. But we usually only add them on the low frequency side. So that means we do not add such high voltage as 30, 60, and 30 hertz because we may have overvoltage. So as soon as a 60 operation, if we still use 460, because that 460 volt already internally have the capability to compensate for the voltage drop in R1 already. And then, so that means we don't want any unwanted voltage rating, and R1 become less significant. So usually at high voltage, the R1 contribution. So at high voltage, the actual voltage drop and the magnetizing become not significant anymore. So the 60 hertz operation is still using 460. But because full voltage, the manufacturer define motor to do, they define 460 volt of operation. This voltage already compensate for you the voltage drop for R1. It's just for low voltage. If you want to continue to use constant flux control, the R1 voltage dropping has not been considered by the manufacturer. So that's why for low frequency operation, you do need to add this one. But for higher voltage, especially for 460, you don't have to do that. So if you want to redo the curve, then that means the curve 34 volt. So if I ask you to redraw the curve, then you need to put in this. Just now we calculate how much voltage, 40 something volt, right? 34 volt. You need to add 34 volt here, away from the origin, and then join the straight line to this point. That should be the way we can calculate the boost voltage at various speed. So that's one of the empirical formula, empirical method we do it. But of course, for low frequency, that is 60 over here, this voltage is still equal to our expected boost voltage. So that's how we easily to calculate the boost voltage, how much it look like. You see this method only all approximation. We never have an exact method to do that. More exact method, you need to go through the modeling for the motor to calculate all the scenario, what kind of boost voltage it should look like. Very speaking, we still haven't calculated excellent voltage drop. It may vary due to various condition. But this is one of the simple method. We are able to calculate the boost voltage. So having said that, then we know that that is quite reliable. We can see that the boost voltage 75% higher than expected. But in this tool, we don't need to do that such a high voltage. So that's why I put a remark to you. We don't do that. So we only tailor-make for the low frequency operation. All right. Any question up to this point? Do you get my point? Why, although we calculate the boost voltage, we don't do that only for low speed. Because for 60 hertz, 460 will already include this kind of phenomenon. So for per phase analysis, let's see that again. So just now we say just now having we mentioned will be for the line voltage, but all the modeling here we're using per phase analysis. So that means the 460 divided by √3 will be the phase voltage. Phase voltage. So that means we convert this one, and they are not equal. So 460 volt, we convert to 265 volt. So the ideal line per phase, that's a per phase value, will be this ratio. So that means 4.4. So that means the per phase voltage, the compensation here, this boost voltage per phase will be roughly about 26 volt. 26. So, so the ideal voltage will be due to this ratio. We can calculate will be about 26 volt for the VF control, and then we had to add on the boost voltage. The boost voltage will be equal to 20 volt. So that's another calculation about per phase, same as before, but we use per phase analysis. Because for practical transformer, we're using the 9 to 9 voltage. But if you want to understand how much is the per phase voltage we perform on each of the motor phase, then you can see that the per phase voltage will be this one, and then the boost voltage on R1 will be only about 20 volt. The same kind of the analysis as before. So, and then let's see how the torque performance look like and without the compensation. So you can see that the torque are proportional to V over F squared, actually. Because, so in here we can see if the torque proportional to V over F squared when the flux is constant. So at 46, without the compensation, we're only using 46. The V over F will be about the ratio 7.6. But if we use the boost voltage, then we are able to increase it up to 13.44. So the torque ratio using the boost voltage, we're able to increase about 3 times. So that's to say, if a motor unable to start, we actually look like we're using 3 times of the voltage to start the motor in order to boost voltage to start. Of course, this is only an estimation. We did not calculate exactly about that. But for low voltage, it never becomes so accurate we can control the motor. So because that's the only simple method to control. So you can see that we're using compensation, we're able to boost up the torque quite a lot. This torque actually is to compensate for the R1 drop. But more importantly, not only compensate for R1 drop, could also compensate for the starting friction and vintage loss. The start of the motor starting friction is quite a lot. When the motor already run to certain speed, the friction becomes much less. So then in the starting friction, we also need to use the boost voltage to compensate. So that's to say, sometimes the boost voltage, although we try to say compensate for R1, but more importantly, we need to test the motor to see how much boost voltage we start. So this boost torque, we also need to compensate for the friction, start of friction. So that also another way we need to look into that. So you can see here, we're using boost voltage, we already boost up to 3 times of the torque as compared to original. So that's why we see that the boost voltage will be quite significant for the motor start, especially in the starting and the low voltage or low frequency operation. So again, you can see that if you calculate the first level, without a compensation, we have 7, and then now the first already look like boost up to 13.44. Yeah. It only look like up to 13.44, right? But because actually between them, we got R1 losses. So in the voltage calculation in here, then we can see that you already go up, have a much higher flux than usual boost on the motor system. You see the boost voltage depend on the voltage on R1. If the torque is small, when you start the motor torque can be small. For instance, when you start the fan slow, the fan slow are proportional to the speed. If the fan slow, then the torque are proportional to speed square. So in theory, if this motor connect to a fan slow and the 0 speed, then the torque will be negligible. For fan slow, we can able to use really small torque to start the rotation. And then so if you use the boost voltage, that boost voltage not only can compensate for R1 losses, can also can boost up the motor flux. Because in this case, the R1 boost voltage made up the 2 important. We had less current for the R1, but we still need to boost up the flux in here in order to compensate for any friction. And maybe other losses. When the motor starting, there's a lot of uncertain losses anyway. So that means we usually cannot only calculate by theory, we say constant wave control. We need to boost up the voltage to compensate a lot of the uncertainty due to the friction and due to the voltage drop on the R1 and also leak gauge and X1 too. So there's a lot of uncertainty R1 and X1. So that's why in here, we just give you a theoretical calculation, how we work out the boost voltage. But you can see that actually there's a lot of the uncertain losses due to the stuffing. So after we finish the wave control, let's see other control method. So most of the controller, they're using this kind of the configuration. So more look like is a AC to DC. So we got three-phase coming in. All the motor drive are DC operated. So you see there's an inverter, is more look like DC to AC inverter system. So between them, we have a DC link. We need to rectify them into DC anyway. So that means our three-phase will rectify into DC and DC inverter into AC. And then we have a different kind of the configuration here. You see, using inverter, you can control the AC quite easily by control the frequency. So we can able to control the frequency control. And then in the old day, how do we control voltage? Then of course, you can using PWM to control voltage. But some other control system, they may think, oh, I can control voltage here by controlling the fire. Then what I propose to you using five-vector control. Using five-vector control, I can control the input voltage. That's why the DC lane voltage here, VI here, can also be adjusted by changing the voltage control. So that means some simple system, you can control this voltage. You can also use inverter to control the frequency. Then you can control VF quite readily. So that's one of the way some control method are using here. But basically, you can see that we are using AC to DC and DC to AC configuration. So simple enough, you can see that there's a really common configuration, a block diagram to do that. Really popular and famous. But you can see that between them, we do have a DC link. So this DC link is quite important. Then we can decouple, we can decouple this frequency to that frequency. You see this frequency from 0 to 60 Hz. But this frequency is 60 Hz. So that's why using this link, all the 60 Hz here disappear from the induction motor. The induction motor can only see a constant DC voltage here or variable DC voltage here. And then we adjust these frequencies, we are able to control the motor at V and F control. So that is what we're trying to do. So the line voltage here can be controllable by using this V control and F control to do that. So that's one of the control method we use for the induction motor, how to control the voltage and the frequencies. So you can see the control method could be like that. One thing would be for the inverter. The inverter cannot control the inverter become a sine wave. The inverter we see today here, we don't control the inverter to produce a pure sine wave. We always produce something called this kind of square wave pattern or pulse width modulation. Of course, there we do a lot of the definition for pulse width modulation. I think you all know about this term now, pulse width modulation. So that means this pulse width are under control in order to control the output voltage too. But if we try to control the frequency for square wave, then you can see that this kind of the square wave will be generated from the inverter. Of course, it's not sine wave, but you can still see that if you use FFT Fourier analysis, you can still see this have a sine wave, a major component, right? So that means this will be similar to what we're trying to do here, to a sine wave. But of course, when we pass through an induction motor, then maybe this sine wave and this motor do have a phase angle between them, depend on the pattern or the load condition. The motor at different time load condition, the phase angle here vary depend on the motor condition. Yes.
Now, is the Oh god, is the magnitude, is the integral of the magnitude the same for both functions over the period?
So the magnitude, the voltage magnitude here depend on another set of equation. This one touch the equation here. But that will be the power electronic force of this. So it is too complicated for you, but we are using this waveform, we are able to control firstly the frequency. This frequency will be easily enough, that's the square wave, we can control the frequency. And the pulse width here, control voltage. You can see that this pulse width, the average voltage will be something in here, roughly, right? You can calculate the average voltage by square wave. So this voltage will be equal to the input voltage V1 to the motor anyway. Of course, this voltage is square wave, not quite a sine wave. As I mentioned before, a motor cell is quite unstable. They not really understand the sine wave or square wave. As long as putting some certain voltage and duration on time, you can produce this kind of thrust. The motor only understand the thrust. So you can see, so it's not really clever, they're really dummy. So what you can see that our motor thrust here, the voltage equal to N d phi dt, right? So that's to say the voltage dt equal to N d phi. The motor only care about what kind of thrust go to the motor. As long as you have certain voltage, certain duration, dt means duration. So certain voltage here, certain dt in here, the motor will think you are, they don't care your sine wave or square wave. They only know is voltage and duration on volt second, and motor or what that kind of thrust in the motor air gap. That's it. Of course, so that is the why we can able to this square wave and apply to a motor without too much problem. But that's only the something. When we apply a square wave, of course, we do have some harmonic thrust, and then harmonic torque. We don't quite like that. So we need to do something. But basically, operation for this kind of motor, if you apply square wave, still work. Because the motor condition is able to control same kind of magnetic thrust. So that's why you can still able to control motor. Motor itself don't care too much about it. But to more strictly speaking, we like to have a nice sine wave to eliminate all the pulsational torque or harmonic torque. So that's what we're trying to do. So that's why we are able to use this kind of the Cauchy square. This kind of waveform is not a complete square. We call it the Cauchy square waveform to control motor. So you see, in the old day, when we don't have a very high speed processor, we can only turn on and turn off the voltage. The reverse voltage by a decent slow pattern, but still not like 60 Hz anyway. Then you can use the 60 Hz to control the voltage. You can vary that 60 Hz to 50 Hz, 40 Hz, have a variable frequency control. Of course, we know that harmonic will be there, but we can still able to control the motor speed. That's how we're trying to do that. But of course, later on, then we gradually move on to have a much better control method. So like the speed control, and we did talk about the speed control, how to control motor in motoring and power regeneration. So what we can do here will be, if we do have a speed loop like that, using the tackle to measure the speed here. And then we try to receive if the motor speed adding the sleep frequency from the motor circuit, sleep frequency. This one adding this one will be the synchronous frequency. If this minus, then this minus this one become a synchronous frequency, that will be minus become the power regeneration. Right? You get the point. So that's why we can using this as a minus to control motor become motoring or power regeneration. Normal operation, this one, I think this one will be the synchronous frequency or the F1 frequency. But however, power regeneration means the motor speed are running faster, higher than the synchronous frequency, we have minus. So very simple control method. We therefore control motor, become a motor or be a generator. So simple, right? Good. Any question? Simple, but able to use what we learned in the past to control motor, to motoring or regeneration. So that means your electric vehicle, we just plus minus, you can control EV will be motoring or power regeneration. or if a wind power, for minus speed come wind power. You see wind power quite special. The wind generation will be, if the wind speed certain location, you can't have too much difference between the location of the motor with the incoming wind speed. They need to quite close to each other. So that means if you want to use maximum power transfer from the wind power to electrical, you need to use a motor to speed up the motor first, so they can catch up the optimal performance location in order to have a maximum power on tracking. So that means for the wind power generation, we use motoring first to motorize the motor to catch up with the wind speed, and then you change back into regeneration. So there's a lot of the theory behind how to develop the wind power generation. Of course, that will be another topic. So this simple method, we are able to control motor to be motoring or power generation by using our well-known equation of this one. So now then, get to a more important point. Now it's getting really, really important. So this really famous torque and speed characteristic, we have seen it for many times. So again, that's a stationary or standstill and starting. That is the synchronous, the zero constant, we already mentioned about that. And then we know the breakdown torque in here. This torque is breakdown torque. And then we haven't shown you the efficiency per motor, but we did sketch the efficiency per motor. That is this purple curve. So the maximum performance of motor exists at that point for most of the induction motor. So this point, you see this breakdown. So usually this percentage are really small, usually less than say 6%. The maximum performance motor usually may be less than 3% of the slip. But anyway, you can see that if you control the motor always working within this region, within that slip, our efficiency of motor will be the best. And also power as well, the motor also power also all force is on that region. That means the slip is small. So as long as we can work on the motor as small slip, the motor will have best performance in terms of torque, efficiency, and power factor. So to do this one, if you want to control motor speed, that's why we need to control the synchronous speed too. So that's the we two together. So that's why we have to use rear control. When the motor required to work at other frequencies, say from 60 Hz, move down to 30 Hz, rotation, you change the synchronous frequency, that means F1 frequency to first 30 Hz as well. So that's the best way we can control that motor to the highest performance, because that is the characteristic for the motor. All the efficiency is highest near the zero constant. When it is small, just a few percent. If it's a few percent, you don't care. 60% is best performance, you control that. 57, 30, 23% different. You know what is that is the best performance. If you want to reduce the motor to 30 Hz, you're still using 60 on the short here, but using low voltage, the efficiency will be really poor because the sleep will be in here, right? Then the efficiency only maybe less than 50%. We won't do that. So if the motor is asked you to drive 30 Hz, you move the synchronous frequency to 30 Hz. So then you get the maximum performance for the efficiency for the motor. So that is curve to show you why we have to use quantum rear control. When we change the voltage to achieve the frequency, why we change the frequency? Because we need to make sure that we operate in this region. Do you get my point? Simple enough, right? That's the most important control concept for induction motor. So that's close to the synchronous. That's the most important. It's close to the synchronous. So after we do that, then we need to start to understand more about the constant rear control, how to do it properly. We still have time, 2 minutes. Don't waste the time. Yeah. So now then, to do this one, so that's to say, if we want to operate at 0 to 60 Hz operation for our induction motor drive system, our F1 frequency need to change accordingly to that frequency control. So we do not only we need to firstly adjust the F1. After we adjust the F1, then we adjust the voltage because we know that we need to use constant react control. So that's how the basic concept. And you see, the frequency we're still using more look like a square wave to do that, but we don't care square wave because the motor itself have a large induction. Even though apply them with square wave, the motor itself is just a very good filter. The square wave, when it goes in the motor, become the filter, become sine wave. So that's why even though input the voltage is more like square wave, but the current for the motor is still quite a sine wave because the motor itself is a good filter. So the voltage control, how do we control voltage and frequency? You use Vok setting control. We use Peter-N as long as we control the voltage second, we delta T, same as the requirement of the sine wave, equivalent to each other. We don't really need to use sine wave. Perfectly we use sine wave, but now that we use paratronic, we cannot generate sine wave. We only generate pulse width square wave. That also be okay. So that's the theory behind why all the inverters are using Peter-N to do that. Of course, you can see that in the market, we do have pure sine wave inverter because they put an internal filter there. But for motor drive system, we don't need to do that. Many motor drive system putting a filter inside is too expensive because we know the motor itself can filter. So we just output all the square wave or Peter-N waveform to drive to the motor. So eventually, you can see this kind of the waveform. The sine wave will be like that. But actually, the sine wave, you can have some formulation. So I think you haven't learned it, but we have formulation convert half the sine wave become the equivalent Peter-N. So this waveform, you can see that this waveform still look like a sine wave. There's a more pulse width. 3% pulse width, so this look like a sine wave. So this waveform will represent a sine wave applied to the induction motor. How electronic we are able to generate this square wave without any problem, only turn on and off. But this voltage for Vok second point of view, for power first point of view, is equal to the same type of the first level. So that's why we use this method to energize induction motor. So that concept we use behind, we call it sinusoidal Peter-N. Sinusoidal Peter-N, we don't cover the formulation here. Let me give you the theory. But if you follow me to do the next level of paratronic or advanced motor, you learn how to do that properly. But for this class, it's too short, only 15 minutes to teach 4 types of motor. You don't have time to teach all. So, all right, any question before we break here? So let's say open books do come in person, bring your PC, everything only cover induction motor from chapter 1 to chapter 2. Yeah. Any question? They will break in word. Not this second, not this second. So most of the over and cover. Okay, see you then. See you.